Feel free to add those to the chat. But the last part of our day today is we're going to be hearing from people who are using AI in their work. So our first talk we have is considerations for testing and evaluation of AI systems, and we have Dr. Emily Castleton, who's a statistician from Los Alamos National Laboratory, who will be presenting for us. So with that, we'll pass it over to Emily and Nikki, if you can unpin me. And yeah, Emily, go ahead and you can share your screen. Everyone has 15 minutes for their talks, and we'll do Q&As after every presentation. So feel free to have questions for Emily. So thanks, Emily. I'll pass it off to you.
Okay, great. Just to check, can you hear me and see my slides?
Yes.
Yes. Okay, perfect. Excellent. So yeah, thank you so much for having me today. As you said, my name is Emily Castleton. I'm a statistician at Los Alamos National Lab. And so my talk is going to be a little high level and some dabs of some technical work. So I'm going to talk about some considerations for testing and evaluation from my perspective of leading two projects where I lead the T&E teams of the AI systems. And then I'll give some highlights of some work that we've done on some of our projects. As we know, AI has had quite a boom in the last couple years, but the boom has primarily focused on model development and putting out new fancy shiny products. But I feel like the shift is happening to being recognizing the importance of testing and evaluation. So there was a report released by Stanford a couple of weeks ago where they talked to all of the AI experts, whatever that means, at Stanford, and asked what their predictions were for the next year for AI. And so I highlighted my favorite line of this, where they say the era of AI evangelism is giving way to an era of AI evaluation. Another kind of data point for how tests and evaluation is currently having a moment from the National Academy of Science report that was recently released. In the introduction, they talk about how the rapid adoption has raised questions and concerns about the reliability, validity, and reproducibility of AI systems. So I do think that there has been a shift finally to recognizing the importance of testing and evaluation. And so I kind of like to set the stage. There's a really great paper by John Burden about evaluating AI evaluation. Um, and he proposes that evaluation is actually prediction. So what we're trying to do when we evaluate an AI system is predict if the system is suitable for its intended purposes. So kind of at the core of evaluation is predicting if the system will perform at an acceptable level on a new task. And obviously, I'm a statistician, and so I think about how things behave in the long term on average. We'll never get to a point where we can fully guarantee how an AI system will perform, but we should be moving towards an approach for how these models will behave on average. So I'm going to talk a little bit about on both my projects. We've kind of focused on benchmark creation. And so this is kind of my high level perspective of how benchmark used to be performed and how the current trends are moving towards something I feel like is more applicable. So in the beginning, benchmarks were just kind of a fire hose of multiple choice questions and answering. And what this actually resulted in doing was testing if what the model knew. So these were tests of knowledge. Does the model know specific facts about different subjects? It also was a bit of a quantity over quality. So to improve a benchmark, you just threw more multiple choice questions into it. The current trend is looking at more holistic benchmarks. So Helm and MMLU have been around for a while, but they are kind of, have a more holistic approach to evaluating how AI system is performing. Another trend are these harder but more realistic benchmarks and kind of tailored to particular subject areas. So I think Health Bench Hard is a great application of this. So this looks at models' ability to answer questions in the medical field. So these are, again, not just looking at general knowledge of a model, but a specific area, and it's looking at how an AI model would interact with patients. So it's more tailored to what a model would actually be used for. And so these are more tests of capability. So is the model capable of performing a particular task rather than is the model knowledgeable of a particular subject area? So I definitely think that, how benchmarks used to be used has led to AI as a field kind of over optimizing for better benchmark results. We see the headlines when a new model is released and it's, a report of an accuracy of how a model performed on all of the benchmarks. And so this leads to, kind of a chasing a state of the art versus actually doing rigorous scientific testing. Um, and so I'm going to talk a little bit about how we've kind of addressed on some of my projects this scientific testing versus chasing state of the art. And I think some of the things that have led to this is there's no uncertainty on metric values. And so there's no accounting for the stochasticity that is inherent in all of these models. There's no attribution of how the model performs and how it relates to some of the metadata of the benchmarks. And so both of these can definitely lead to a false perception of a particular model's dominance. So as an example for these two things, I'm going to use the Visual Task Adaptation Benchmark, or VTAB. This is a pretty popular computer vision benchmark out in the open. And so just as a little background of the benchmark, there are three categories of images that are in this benchmark. So we have the natural images, which are, pictures you take with a camera, specialized images, which are usually medical images, and then structured images, where they have kind of boxes and circles and things set up in an array. So we're using this benchmark. This is some work that a student has performed on our project. And so I'm going to spend a little bit of time talking about this plot because it is my favorite plot that has ever been made. And so what this plot shows is, again, we have these three categories of images: structured, specialized, and natural. And how the benchmark compares models is with an unweighted average of the accuracy of the three different categories. What this plot shows is the range of all possible weights that you could put on the different accuracies. So if we look right in the middle of this triangle, this would be the unweighted average. So putting equal weight onto all of the three different categories. And in each of the corners, this is putting all of the weight onto one of the particular categories. So another thing that this plot demonstrates is we were also put uncertainty on the metric values. So what we're saying here is if there is a gray space in the triangle, then there is no clear winner. There is statistical overlap between the top two or top three models that are being performed. And so if we look at this, the area of the triangle represents which model was dominant for that particular combination of weight values. And we can see that the top model, at least at the time that we did this analysis, was subrotation 100%. It occupies a big swath of the triangle, which means that was the most dominant model for that combination of weights. The other thing is that most of the triangle is gray. And so most of the triangle, there is no clear dominant winner. The last thing I'll point out about this, which kind of ties to, the importance of looking at metadata. If we look in this corner over here, there's a little pink area. So if the type of image of interest is structured and you put all of the weight on the structured values, the top performing model is the model rotation, which is actually the sixth ranked model on the leaderboard. So by breaking out the performance based on this metadata, we're able to see that, for some certain types of images, one model does perform better than the other. which is not something you would be able to see just by looking at the unweighted average and models ranked that way. Okay, so that was a little bit about some work that we've done in the vision um, task. Now I'm going to talk a little bit about multimodal foundation model, and particularly within seismology. And so one of the models that was developed is a multimodal model that takes time series, text description, and maps from the seismic domain. So I have kind of an example over here of the three different modalities for an earthquake that happened near Taiwan last year. Um, and so we have interest of building a model that can take all three of these data modalities and make some detections of an earthquake arrival. So when a seismic event happens, the seismic wave travels through the medium and then reaches the seismic sensor. And the time at which it reaches that first sensor, we call that the P wave. So what I'm going to kind of talk about is the benchmarking that we've used to evaluate this model. And so there's a popular seismic benchmark called SeisBench that has, again, this is the quantity over quality approach to assessing how well the benchmark or how well the models do, where there's a lot of waveforms that go into determining how well the model does. We're particularly interested usually in underrepresented signals, and so that kind of dominant or the performance on those signals can get masked out. And it's also really computationally expensive if you have a ton of waveforms to assess. So the approach that we took was starting with this size bench and then creating a down select on the waveforms that were there to create what we're calling diver size. And so we're reducing redundancy, but still having that coverage of the variability. And it's a faster evaluation because it's less waveforms to feed through the models. So again, we're leveraging existing benchmarks data. We kind of separate the waveforms into earthquakes or noise. And kind of the novel approach that we're taking here is from the earthquake data, the way that we sample the data that will go into the benchmark is by fitting an autoencoder and then sampling from that latent space from the autoencoder. So this is just kind of a pictorial view of the creation of the diver size. And again, so we have the earthquake waveforms, we fit the model, we then divide up the latent space to do a uniform sample across that. And so again, I feel like this approach, this is very novel to fitting a model to determine the waveforms that will go into the benchmark. But thinking a little bit more, putting a little more thought into what how we assess these models and what waveforms go into that. Um, okay, so kind of the last thing I'll talk about, and I apologize, I'm not going into any detail on any of these technical issues. We do have papers out for most of them. I just wanted to give kind of a flavor of kind of the direction that we're taking on the projects for how to assess models a little better. And so the last example I'll give is using bespoke benchmarks that can lead to more efficient training and more informed results. So we have found that little thought when someone is developing a model is put toward the metrics that's used to test it or the cost function that's used to train them. And so we have some results that show that if your cost function or your metric is more tuned to the task of interest or even just the application area, this can lead to better models with less data. And so, what we really want to know is if the model is appropriately answering the questions that we would like the questions of interest that we would like the model to answer. So again, I'll just show kind of a quick example of this. One thing that we're interested in is what's called autoregressive rollout. And so this is you have a multiphysics simulation. You give the model the first time step of the multiphysics simulation, and you ask it to predict the next subsequent time steps. So in this example here, we have our ground truth. This is what comes out of the multiphysics simulation. And then we have there was three models, we'll call them tiny, big, and large, that given that initial state, were asked to roll out to time steps 16, 17, 18, and 19. And so just looking at how the model does, none of them are like super great, right? Tiny is just completely random. Big is also kind of smeared out everything. Again, these models were fit with MSE. MSE does tend to like just smear over features. Um, and the large, does the best of the three, just kind of by the eyeball norm, I'd say. Um, so using MSE to compare these models, and so here I have in the red boxes, these are the time steps that I showed you on the previous slide. So MSE shows that tiny does the worst. We saw that. But it also shows that big and large, it looks like their performance is pretty comparable. Um, but if we go back and look, big does worse than large. So we developed this new metric, and again, I won't go into details of it, but it's using the correlation coefficient at various scales. And we can see that, it actually accurately picks up that tiny's pretty random. Big isn't also doing well, but that the large one is doing better. And so again, I don't know that I'm going to convince you that this is the right metrics to use in this particular instance. But I just wanted to give an example of, putting more thought into the metrics that are used to evaluate or even train the model can lead to more intuitive results. All right, I'm a little over time, so I'll wrap up with kind of what I feel like is the future of evaluation. And that's, defining what the specified capabilities are that we want these models to do, and then more holistically evaluating them. I really like this figure that I took from the DoD's CDAO, where it shows that, correctness is an important thing for models, but there's so much other stuff that's going on. And what we should really be asking is this model appropriate for my application? So I will stop talking and happy to take questions.
Thank you, Emily, for the presentation. So we have about 2 minutes for Q&A. So do we have any questions for Emily?
And I will apologize, I can't see the chat from the screen. So if you ask a question in chat.
Sure. I will let you know if I
Okay,
see
thanks.
any question in the chat.
Emily, I had a quick question. I was wondering in your studies and experiments, if you found out what would be good ways to evaluate non-deterministic, if a specific question can be answered with multiple ways,
Mm,
like how do you evaluate the effectiveness of the same model, but answered in different ways, for example, like because they won't have convergence in the same statistical sense or like a numerical sense, right? There's no golden answer in that sense, right?
yeah. Um, I mean, so honestly, I feel like the best way to do that is a way that assumes that you have white box access to the model, and that's to look at the log probabilities out
Hmm.
of the model. Um, Short of that, a lot of these frontier models, we just don't have that, and so I think there has to be some sort of ensemble approach to looking at the results. And so that makes it very computation expensive, and there's no way to fully explore the space.
Sure.
But I feel like without the white box access, that's the best we can hope for.
Got it. Yeah, the approach that I was looking into is people evaluating workflows to see if workflows
Mm,
have convergence rather than the actual final answer.
that makes sense.
Uh,
Yeah, that's
yeah,
still now you have to explore even more more.
exactly.
Yeah,
Yeah, even more space.
yeah,
Thank you,
yeah.
Emily.
Uh-huh.
More questions for Emily? If none, please join me in thanking Emily for wonderful presentations. And since Emily, you mentioned that there are papers already published.